In this video, we're going to discuss the standard reduction potential. Standard reduction potential is defined as a measure of the tendency of a chemical species to acquire electrons and thereby be reduced. Each species has its own intrinsic reduction potential. The more positive this potential, the greater the species' affinity for electrons and the greater its tendency to be reduced. Let's look at a galvanic cell here. We've seen a galvanic cell here between zinc and copper. If we make this galvanic cell, hook the two half reactions up, the two half cells up, electrons will spontaneously begin to flow from the zinc to the copper. They'll always flow in this direction. And this is because copper has a greater standard reduction potential. It has a greater pull or affinity for electrons than does zinc. So the electrons will always flow towards the copper and away from the zinc when these two half cells are paired up. So how do we tell what a standard reduction potential is for a given half reaction? Well, thankfully, a lot of these have already been calculated for us. You have a much larger table in the appendix of your textbook, but here's a short table. As you can see, the standard reduction potentials, which are measured in volts, they get larger and more positive as we go up the table. So our half reaction here, the fluorine half reaction, has the greatest standard reduction potential of anything on this table, whereas lithium has the weakest or the lowest standard reduction potential. So if you made a galvanic cell between fluorine and anything on this table, fluorine would be reduced and the other thing would be oxidized. If you made a galvanic cell between lithium and any other half reaction here, the lithium would be oxidized and the other half reaction would be reduced because it has a greater standard reduction potential than lithium. Now we saw copper and zinc. You can see here's the copper half reaction, and copper's standard reduction potential is 0.34 volts, whereas zinc's standard reduction potential is a negative 0.76 volts. And so therefore, since copper has a greater standard reduction potential, it will be reduced, the zinc will be oxidized when you make a galvanic cell. Now we'll talk more about this in just a second, but notice this hydrogen half reaction is assigned a standard reduction potential of 0. We'll come back to that in a minute, but that's important to note. So standard reduction potentials are determined experimentally. In order to determine it, you can't just look at one half reaction. You have to pair that half reaction up with something else. So potentials can only be measured in pairs, which is why we need to establish some reference point for our half cells. This reference point is what we call the standard hydrogen electrode, and that's that hydrogen half reaction that we were just noting. So the standard hydrogen electrode is assigned a 0 value, and these other values, these other standard reduction potentials, are measured against that hydrogen electrode. So we make a galvanic cell between hydrogen and some other species like copper, and we measure the cell potential against by pairing those two up, and that's how we get these values. So we'll speak more about that in just a minute in a bit more detail. So the standard hydrogen electrode looks something like this. You can see over here it's on the right side of this galvanic cell, but you could put it on the right or left, it doesn't matter. So here we have a glass tube, and through this glass tube we bubble in hydrogen gas. So we have to have hydrogen gas, and we bubble it in at a pressure of 1 atmosphere, and then we have a solution which contains hydrogen ions. So this would be some acid solution, some strong acid with a concentration of 1 molar. Now this half reaction does not have a metal that we can use as an electrode, so we have to use a inert electrode, a platinum electrode, to conduct the electricity down into our solution. So this is the general makeup of the standard hydrogen electrode. To get those standard reduction potentials, we would pair this standard hydrogen electrode up with some other half cell. It doesn't matter which one it is, and then we would measure the voltage or the potential difference between those two. and that would give us the standard reduction potential of this other half cell. So we'll talk more about that here. The standard hydrogen electrode is paired up with another half cell to make a galvanic cell. We just showed you that. Under standard conditions, which we defined as 25 Celsius, 1 molar solutions, and 1 atmosphere of our gas pressures, the galvanic cell is hooked up to the voltmeter and the cell potential is measured. Remember, the standard hydrogen electrode is assigned a potential of 0, so the standard reduction potential for the other half cell is whatever our cell potential is. So whatever that voltmeter reads is the standard reduction potential of the other half cell that's paired with the standard hydrogen electrode. Let's look at an example of that to help illustrate. Let's say we wanted to measure the standard reduction potential of the zinc half reaction. So we have the zinc half reaction. We want to measure its standard reduction potential. We would make a galvanic cell between the zinc and the standard hydrogen electrode. When we pair those up, the electrons in this case would flow from the zinc. They would begin to spontaneously flow from the zinc to the standard hydrogen electrode. If we hooked up a voltmeter, we would see that the voltmeter read negative 0.76 volts. So the negative sign tells us that the electrons are flowing from the zinc to the standard hydrogen electrode. That tells us that the standard hydrogen electrode has a higher standard reduction potential because it's pulling the electrons towards it. The voltmeter reads negative 0.76 volts. So this number here is assigned the standard reduction, is assigned the standard reduction potential of the zinc half cell. So if you look back on our table, if we find our zinc, we can see that its standard reduction potential is negative 0.76. So when we paired it up with the hydrogen, hydrogen has a greater standard reduction potential, so the electrons flowed from the zinc to the hydrogen, and the potential difference between those was 0.76 volts. The negative sign means that it was oxidized and the standard hydrogen electrode was reduced. Let's look at another example to help illustrate this. Let's say we wanted to measure the standard reduction potential of the copper half reaction. We would again pair that copper half reaction up with the standard hydrogen electrode. We'd connect the two half reactions to make a galvanic cell. In this galvanic cell, however, the electrons will spontaneously flow from the hydrogen to the copper. So this tells us that the copper has a greater, more positive standard the copper has a greater standard reduction potential, a more positive standard reduction potential than the hydrogen. So the positive standard reduction potential that we see here, the positive cell potential, indicates that the half cell undergoes reduction when paired with the standard hydrogen electrode. And if we hooked up a voltmeter, we would get a potential difference between these two half cells of positive 0.34 volts. So that tells us, the positive sign tells us that the copper half reaction is going to pull the electrons towards it, so it has a greater standard reduction potential, and the standard reduction potential for the copper would be 0.34 volts. So if we look on our table here, you can see the copper half reaction is above the standard hydrogen electrode, so it's going to be reduced when paired up with this guy, and the standard reduction potential is 0.34 volts. So now that we've looked at how these standard reduction potentials are determined experimentally, why do we need to know what they are? Why are they useful? Well, standard reduction potentials, by comparing the standard reduction potentials of an anode and a cathode, we can calculate the overall cell potential for a galvanic cell. And we'll look at that in another video. If we make a galvanic cell with any two species, it doesn't have to be the hydrogen electrode, but if we make a galvanic cell between zinc and copper, as we saw, we can determine which species or which half reaction will be oxidized and which will be reduced by comparing their standard reduction potentials. So these standard reduction potentials gives us a lot of information when we're making a galvanic cell. It tells us what our anode will be, what our cathode will be, and what the potential difference between those will be. even if we don't use the standard hydrogen electrode. And we'll look at how to calculate that in another video.